Okay, so here are the notes for isotopes. So what is an isotope? So an isotope is an atom of an element with a different number of neutrons. Okay, so as we're going through this, go ahead and follow along by filling in your handout. So what we have here is we have three isotopes, right? We have three isotopes of a simple element called hydrogen. First isotope is called protium. The second isotope is called deuterium. And the third isotope is called tritium. Now, what I want you to focus on here is I want you to focus on what the definition says, that an atom is an element of an atom of an element with a different number of neutrons. So if you take a look at the first one, right, which is protium, you can see that the nucleus has 0 neutrons. Okay. When you jump to hydrogen 2 or deuterium, you notice that inside of the nucleus, now we begin to see 1 neutron. And as we jump to tritium, right, you'll notice that tritium has 2 neutrons in the nucleus. So we have two neutrons in the nucleus for tritium. We have 1 neutron in the nucleus for deuterium, and we have 0 neutrons in the nucleus for hydrogen, or for protium. So as you can see, what's consistent across all these three isotopes is the number of protons doesn't change, the number of electrons doesn't change, but what is changing is the number of neutrons. Right? So that brings us to our left here. Okay, the number of protons for isotopes are the same. So we have the same number of positively charged protons. That does not change. Okay, we have the same number of electrons. Those carry the negative charge. So those do not change. What is changing, however, is the number of neutrons, because we have a different number of no charged neutrons. Okay, so when we're talking about isotopes, we're simply talking about an atom when you have different number of neutrons. Now, even though these have the same number of protons and electrons, right, they're still the same atom. They're all still hydrogen. Regardless of the fact that they have different number of neutrons, because they have the same number of protons and they have the same number of electrons, then all isotopes properties remain the same. They will not react different. They will not behave different. They're all going to behave exactly like one another. Again, the only difference being the number of neutrons. Now, when we represent isotopic notation or an isotope, we do it using something called isotopic notation. Isotopic notation is just a way to write isotopes, right? We have a basic model that we follow here. We have the atomic number, which goes down in the bottom left-hand corner. And then we have the mass number, which is in the top right-hand corner, left-hand corner, okay? The X here represents the symbol of the element. So whatever the element is, you're going to use the chemical symbol from the periodic table, and then we're going to write the isotopes according to this model. For example, the chemical symbol for hydrogen is H. So if I want to represent the first isotope, I'm going to write it as follows. Hydrogen has an atomic number of 1, and the first isotope, protium, has a mass number of 1. Okay. If we jump to deuterium, right, here's what we see. Deuterium also has a mass number of 1, right? Atomic number of 1, because the number of protons does not change. However, the mass here is now changed. It has now become 2, so I would write it as 2 in the top left-hand corner. Okay, and then finally for tritium, be the same thing. The atomic number, once again, does not change, right? But the number of particles in the nucleus does change. Now we have 3, right? So these would be the isotopic notation of each of the isotopes of hydrogen. Now, pay attention to what's going on here, right? In the first atom, right, isotope, we see that the nucleus has only one particle, okay, right here, the proton. So because it only has one particle, it has an atomic mass of 1. In the second one, in deuterium, you see that there's 2 particles in the nucleus, 1 neutron and 1 proton. As such, the mass is now increased to 2, okay? And then finally, in the third isotope, we see that there are 3 particles in the nucleus, which means the atomic mass for this isotope has now increased to 3. So as you can see, an atom derives its mass from the number of particles in the nucleus. Rule of thumb is 1 particle has 1 AMU of mass. So 1 particle equals 1 AMU of mass. Now, that's not the case, right? They're slightly off by 0.0007 of an AMU, but general rule of thumb is that 1 particle equals 1 atomic mass unit. So if you have 3 particles in the nucleus, you have an atomic mass of 3, give or take. Okay. Excuse me. Now, as we go through the process, right, here's what we know about isotopes of a given atom that exists at the same time. What does that mean? That means that all isotopes of any element are always present. What that means is that doesn't matter what the element is, how much of the element you have, if that element has multiple isotopes, all those isotopes are always present in any sample at any given time, anywhere in the universe. Isotopes always exist in the same ratios. What that means is that every element has exactly the same ratio of isotopes to any other sample of the same element. For example, if I was to get 100 grams of copper from Europe, and I compared that to 100 grams of copper from the United States, right? If I was to analyze each one of those copper samples would have exactly the same amount of isotopes, or the same number of isotopes, in the exact same ratios as any other, right? So these isotopes are always present and they're always in the exact same ratios, okay? And then lastly, the ratios are determined by percent abundance. Ratios of isotopes are determined, and there's 2 ways to call this, right? Just by either the relative or percent of abundance. Okay, and I'm going to abbreviate that. Now, what is relative or percent abundance? So when we're talking about percent abundances, here's what I'm talking about. On the table in your notes, you have the list of 3 isotopes of hydrogen, H1, H2, H3. Then you have the name, which is protium, deuterium, and tritium, which we've already discussed. And you have the atomic mass of each one. Remember that since each one is differing in the number of neutrons, right, the atomic mass is changing as a reflection of adding more neutrons to the nucleus. For example, the atomic mass of hydrogen 1 is 1.0078, hydrogen 2 is 2.0141, and hydrogen 3 is 3.0160. So those masses are a reflection of the mass or the amount of particles in the nucleus. So for hydrogen 1, we have 1.0078, okay? Then we have hydrogen 2, and then finally we have hydrogen 3. Okay, so those are our masses for each isotope. Now, as we go through, you get finally to natural abundance, which is the same thing as percent abundance, which is the same thing as relative abundance. Okay, what we see here is that hydrogen 1 has a 99.99 or 9885% of abundance. What does that mean? That means that if I was to get a sample, right, a jar, and fill it up with hydrogen, right, and I was able to analyze each individual atom, I would see that 99.9885% of all the hydrogen in the jar would be isotope hydrogen 1. They would be in that format, right? So if I was to look at this jar and was able to look at each individual atom, the vast majority, or 99.999885% of those atoms would be in the format of 1 proton and no neutrons, or hydrogen 1 isotope. Okay? Going to hydrogen 2 is the same thing. If I was to take a look at all those atoms, right, I would find that 0.0115% of all of those atoms would be hydrogen 2 isotope, right? And then finally, we take a look at something like the hydrogen 3. And what that tells us is that the amount is so small, it is insignificant, right? It does not register because the quantity is so small that it's not even, it's a number too small to have any effect on any of the data here, right? In this situation, this would be the most rare, and the top one, or the hydrogen 1, that would be the most abundant. Okay. Now, there's two ways to show isotopes, all right? And one way is the table that we have here that has all the information that we need. And the other is called an hydrogen isotope pattern, right? What that shows us is basically a bar graph, right? The bar graph is kind of giving us an idea of how many isotopes exist within a given element, and of those isotopes, which one is the most and least abundant. Now, in this situation, what we see here is is that the vast majority of all hydrogen exist as hydrogen 2. So we only see, as hydrogen 1, excuse me. We only see the 1 bar, right? Now, even though hydrogen has 3 isotopes, we should see 3 bars. However, these numbers are so small that they don't even register on the graph. So when you look at a chart of a hydrogen isotope pattern, you only see 1 bar. Now, that's not going to be the case. Different elements have different isotopes. They all have different abundances. So every element is going to have its own unique set of isotopic patterns and their own set of isotope percent abundances. Some elements will have 1 or 2 isotopes. Other elements I've seen can have up to 17 isotopes. So it just depends on what element you're working with and how abundant each isotope is. Now, why does this matter? Well, this matters for the following reason, right? When you take a look at an element on the periodic table, you see lots of information. You see the atomic number, which gives you the number of protons and electrons. You see the atomic symbol, or the element symbol, which is H in this case, and the name on some periodic tables. What we're focusing on is the atomic mass. Now, hydrogen has a mass of 1.008, right? If you notice, the mass is here, right? Let me get my little arrow here. The mass is here. None of those add up to 1.008. There's one in the first one that's very close, and you'll see why in just a minute. But where does the 1008 come from, right? If I was to just add up the number of protons and electrons for any element, I would never get this number. And the reason you don't get this number is because this number takes into account all of the isotopes that exist within a given element. So let's take a look, right? If I was to take a look at hydrogen 1, right, the first thing I'm going to do is I'm going to take a look at that percent abundance, okay? And I'm going to convert that into a decimal. Because remember that a percent is out of 100. So in order for me to convert a percent into a decimal, why is this? Okay, I don't know why it's not letting me erase, but we'll move on. Looking at this particular hang on, I'm sorry. Okay, sorry guys, I'm having technical difficulties here. I don't understand why my pen keeps reverting to text. Let me see what's going on here. Okay, I think I got it. Anyway, oh goodness. Okay, it got shifted. I don't know what happened, but we'll deal with it later. If I have a percent abundance of 99.9985, right, I'm going to take that and I'm going to convert it to a decimal. So in order to do that, I'm going to move the decimal over 2 times in this direction, because essentially what I'm doing is dividing by 100. So then this number becomes 0.999885, right? That becomes my decimal of that percent, okay? If I do the same thing for the other percent abundance, which is 0.0115, and I move my decimal over twice in this direction, well then I become, or this number becomes 0.000115, right? So now that I have those numbers converted into their decimals, right? Because remember that these masses exist at these percentages, I'm going to multiply each one by that mass. So this one gets multiplied, the 99.9985, by 1.0078. And then this one gets multiplied by 0.000115. Now, if I multiply this out, I'm going to end up with 1.00768. Now, if I do the same thing for the second one, let me see here. Try this again, see if it doesn't get messed up. There we go. That's actually going to be multiplied by 2.0141. Apologies for that. The technical difficulties of my tablet here kind of got me all screwed up here. So 0.000115, I'm going to multiply that by 2.0141, and I'm going to end up with 0.000231. Now, if I take these numbers and I add them up, right? I end up with 1.0079. Okay, this number represents the number on the periodic table, and if I was to round up to this place right here, this becomes 1.008, which is the same number that we have here. Okay, so the reason that this is important is because these numbers, right, these isotopes help us determine the average atomic mass of a given element on the periodic table. Okay, go ahead and finish copying this up. That's it for today.